Hello everyone, welcome to Brain Blitz Audios. Today in this episode of NEET preparation, we'll be continuing our surge into previous year questions of physics and medical entrance examinations in India. Today, we're going to deal with the chapter Electromagnetic Induction. This is the 6th chapter in the grade 12 syllabus for physics in CBSE. Now, let's look at our first question. A conducting ring of radius 1 meter is placed in a uniform magnetic field, B, of 0.01 Tesla, oscillating with frequency of 100 Hz, with its plane at a right angle to B. What will be the induced electric field? So let's look at this question. The radius is 1 meter. The magnetic field B is equal to 0.01 Tesla, and the frequency F is 100 Hertz. And this conducting ring is placed with its plane at right angle to the magnetic field. So therefore, we can represent the scenario like this. So here's the plane of the conducting ring, and you can see that the magnetic field lines are going into the plane. So they are perpendicular to the plane of the conductor ring. So we know that R is 1 meter, B is 0.01 Tesla. We know that frequency is equal to 1 by time. So therefore, 1 by time period is equal to 100. So therefore, time period will be equal to 1 by 100. So 1 by 100 seconds is the time period. Now, we need to find out the induced electric field. Now, for induced electric field, we use the formula line integral of E dot dl is equal to the change in flux, that is d phi by dt. Now we know that flux is equal to B dot A. So therefore, we will have dB by dt times A as the right-hand side of line integral of E dot dl. Now here we're looking at a conducting ring. The conducting ring means the wire is along the circumference of the circle of radius r. So it is the circumference. So we can say that the electric field times 2 pi r is equal to the area, which is pi r square, times dB divided by dt. So let's calculate the values of dB and dt. Now dB can be calculated as final magnetic field minus initial magnetic field. So since this is oscillating, the conducting ring is oscillating, so therefore the final will be 0.01 Tesla and the initial will be the exact negative, so minus 0.01 Tesla. So therefore the value of the change in magnetic field, this will be equal to 0.02 Tesla. Time period. Now, since it's oscillating with a frequency of 100 Hertz, here we're taking dt as t by 2. So the time taken in order to complete a half oscillation is t by 2. So using that formula, we're moving along. So the value of t is 1 by 100. So it'll be 1 by 2 times 100. That will be the value of dt. Now let's keep it as 1 by 2 into 100, because when we're calculating the value of electric field, this form will help us out. So now we just need to find E, which is the induced electric field. So therefore E is equal to pi r squared divided by 2 pi r times dB by dt. One of the r's gets cancelled, the pi's gets cancelled, so we have r by 2 times dB by dt. Let's plug in the values. R is 1 meter, divided by 2 times the value of dB is 0.02 divided by the value of dt is 1 by 2 into 100. So that means it becomes 1 by 2 times 0.02 into 2 into 100. The 2's get cancelled. 0.02 times 100 is equal to 2 volts. So the right answer is 2 volts. And which of these options is containing the right answer? It is option B. So by using the formula for electric field, line integral of E dot dl is equal to d phi by dt, we were able to find out the value of the induced electric field, which is equal to 2 volts. So that is option B. Now let's look at this second question. A magnet is made to oscillate with a particular frequency, passing through a coil as shown in this figure. The time variation of the magnitude of EMF generated across the coil during one cycle is given by a graph. Now the graphs are given in the next page. Let's view them. So these are the 4 graphs, which are our options. We need to find out which of these is the right graph for the periodic motion given here. Now, we all know that the EMF induced has the formula minus of d phi by dt. And this question is basically about direction, so there's no need for understanding or finding out the magnitude, just the direction would do. So since the formula is minus d phi by dt, so when d phi is positive, the EMF is negative. And when d phi is negative, then the EMF is positive. So which are the conditions when d phi gets positive and d phi gets negative? D phi becomes positive when the field lines come into coil, and when d phi is negative, field lines come out of the coil. So in this cycle, from 0 to t by 4, the magnet tries to move into the coil. So therefore, at these times, the EMF is positive. And from t by 4 to t by 2, the magnet is moving away. So therefore, the EMF is now negative. When t by 2, when we take the time period from 3t by 2 to 3t by 4, that means from half to 3/4 of the time period, again, the EMF becomes positive. And from 3t by 4 to the total time t for one oscillation, at this part, the EMF is again negative. So these are our 4 scenarios. If we look at our options, you can see that the first part, you can see that in the first graph, the first part is positive, the second part is negative, the third part is positive, and the fourth part is negative, just as we found out. So therefore, option A is the right option. In option B, it says that the EMF becomes positive only for a brief period of time, which is wrong. In option C, again, there are only positive waves, again, which is incorrect. In option D, it says that the negative waves come together and the positive waves are pushed farther apart. So therefore, option D is also incorrect. The right answer is option A. EMF is alternating from positive to negative, depending on the direction of the magnetic, depending on the direction of the bar magnet. Now, let's look at this question. So a metallic ring is dropped down, keeping its plane perpendicular to a constant and horizontal magnetic field. The ring enters the region of magnetic field at t is equal to 0 and completely emerges out at t is equal to t is equal to capital T seconds. The current in the ring varies as. These are the options given. So since this question has no diagram, let's draw a diagram. So basically, we have a horizontal magnetic field. This is constant. Now let's consider this as B. And you can see that there is a metallic ring which is dropped down. So this is actually perpendicular. This is actually perpendicular to, what I meant is that when the ring is dropped down, it's dropped in such a way that the magnetic field lines pass through it in a perpendicular manner. So it's perpendicular to the field of the ring, the magnetic field lines. So when it comes to electromagnetic induction, a current is induced when there is a change in flux. Now, at time t equals 0, the ring started to enter the magnetic field. So therefore, there is a change in flux. So therefore, we found out that there will be an increase in the current present in the ring. After some time, you notice that the metallic ring is now completely inside the magnetic field. So in this case, you find that even if the ring drops down, the magnetic field stays constant because this is falling under a constant and horizontal magnetic field. So we have a constant flux, so therefore 0 current. However, the situation changes when the metallic ring starts to move out of the magnetic field. So this is acting under gravity, which is independent of the magnetic field. So once the metallic ring starts coming out, there is again a change in flux. So therefore there is current induced in this scenario. And by time equals t, the ring has completely emerged out of the magnetic field, and henceforth there will be no change in flux, no flux in fact. So therefore the current drops down to 0. So this is our scenario. And if you're looking at our given graphs, the increase in current at both sides is correctly shown by our graph A. So option A is the right option. In option D, it shows that there is a constant current between the two ends. So this is only possible if there is constant change in flux, but we know that the magnetic field is constant, so therefore this cannot occur. Option D also cannot occur because what this shows is that while the ring is entering the magnetic field, it increases, and then the current is constant. However, for current to be constant, we have to have a constant change in magnetic field, so which is not happening. So this option D is also incorrect. In option B, initially there's an increase in current, but however, in this graph, it is wrongly shown that as we remove the flux, as we remove the magnetic ring away from the magnetic field, the current induced is negative, which is again incorrect. The right answer is option A, in which the graph shows an increase in current at the times when there is a change in flux, as if when the magnetic field ring enters, and when the ring leaves. So that is why option A remains the right option. Now let's look at this question. Which of the following conclusions can be drawn from the result line integral of b bar dot dA bar equals 0? Now, if you look at this law closely, we know that this is the Gauss's law of magnetism. And we also know that B dot, so the magnetic field multiplied by the area of cross-section represents the magnetic flux passing through. So therefore, the magnetic flux of a closed surface is equal to 0. So area cannot be 0 in the case the area cannot turn to 0 because we're doing it for a single area of cross section, which is constant. So therefore, since phi is 0, so B dot A has to be 0. Therefore, we can conclude that B is equal to 0. So that means the net magnetic field is equal to 0. Now, what does this term mean? The net magnetic field is equal to 0. It means that in a closed surface, we will have both positive and negative fields. So the fields will be in opposite directions. And the sum, which is present, so the sum of positive and negative magnetic charge, which is what we call this, is equal to 0. Now, this is only possible when there are areas in the field, in the closed surface, where the field is predominantly positive, so called a positive pole. And there'll be also areas in the closed surface where the negative charge is dominant, negative magnetic charge, which means a negative pole. So that means the magnetic poles formed in a closed surface, these are equal and opposite. Now, what does this prove? This proves the fact that there are no monopoles. If magnetic monopoles did exist, then the Gauss's law of magnetism will be proved wrong, because if there's only one pole in a closed surface, then that pole generates some magnetic field, which is not 0, and therefore the Gauss's law of magnetism will be wrong. But Gauss's law of magnetism is experimentally proven, so therefore we know that the situation where monopoles exist does not occur. So magnetic monopoles do not exist. That is the correct conclusion which we can draw from the Gauss's law of magnetism. Option A, magnetic field is 0 everywhere, is incorrect because we have objects that can be magnetized. And option C, magnetic lines of force do not intersect each other. Again, this is a different law, not exactly related with the Gauss's law of magnetism. A current produces magnetic field, which is again the whole idea behind electromagnetic induction and also electromagnetism. So therefore, it is not a part of Gauss's law of magnetism. So the right conclusion is conclusion B. Magnetic monopoles do not exist because of the fact that the total flux passing through the closed surface is 0. Moving on, let's look at this fifth question. A wheel has 10 metallic spokes, and each of these spokes are 0.5 meters long, and they're rotated with a speed of 120 revolutions per minute. And this is done in a plane normal to the Earth's magnetic field at a place. If the magnitude of the field is 0.4 G, the induced EMF, which is what we have to find out, between the axle and the rim of the wheel is equal to. So we need to find out the magnetic field caused by the metallic spokes. So in this question, we have the length of each spoke is 0.5 meters, and the speed is given as 0.4, or not 0.4, it is 120 revolutions per minute. So we can, think of it as 120 times 1 revolution per minute. So in 1 revolution, the distance covered is 2 pi divided by the total number of seconds in a minute is 60. So that is how we define omega, or angular frequency. And we have the magnitude of the magnetic field, the modulus of B, as 0.4 Gauss, which we can write as 0.4 into 10 raised to minus 4. No, I mean, is 0.4 into 10 raised to plus 4 Tesla, because 1 Tesla is 10 raised to 4 Gauss. So now we need to find the value of the induced EMF. Now the induced EMF, which is present here, is not the kind of EMF that you usually use, the kind that comes due to translatory motion. Here, the metallic spokes are actually rotating, so therefore we use rotational EMF. And this has a separate formula, which is B is equal to, EMF is equal to B times omega times L square divided by 2. So now we can write the value for B. So 0.4 into 10 raised to 4 times 120 into 2 pi by 60 times 0.5, the whole square. And the whole divided by 2. Do not forget it. So now what happens? 60 cancels out. So leaving a 2. 2 times 2 is 4. So we can write 4 into 10 cubed times 4 pi. 4 pi can be written as 4 into 3.14. 5 squared is 25, so 0.5, the whole square will be 0.25. And then whole divided by 2. So now we can cut off one of the 4s, so we get a 2. 4 times 2 is 8. 8 into 3.14, we can write it as 314 into 10 raised to minus 2. And we can write the other value as 25. So into 10 raised to 3 minus 2 minus 2. So what we get, so we can just multiply 8 and 25. 25 times 8, it's actually quite easy because 4 25s gives you 100. So 8 25s gives you 2 times 100, which is 200. So we'll have 200 times 314 times 10 raised to minus 1. So that's divided by 10. So we'll get the EMF as 20 times 314, because 200 divided by 10, that's 20. So 314 times 20. So let's do 314 times 2. 4 times 2 is 8. 1 times 2 is 2. 3 times 2 is 6. So it'll be 6280, the value of the EMF. So 6280 volts. However, we can convert this into 0.628, that is pulling the decimal 4 steps backwards. So therefore 0.628 into 10 raised to minus 4 volts. So this is our required answer. And do you know which of these is the right answer? Option B, 6.28 into 10 raised to minus 4 volts. So actually this becomes 62800, and then when we pull back 4 steps, we get 6.28 into 10 raised to minus 4 volts. So that is how we solve this question. So it's just basically 2 pi, so 2 into 3.14, that's 6.28 into 10 raised to minus 4 volts. So option B is the right option. Option A and C refers to 4 pi, which is not the correct answer. And option D has a difference in the exponent, which is again incorrect. The right answer is option B, 6.28 into 10 raised to minus 4 volts. Now let's move on to the final question. The magnetic flux through a circuit carrying a current of 2 amperes is 0.8 Weber. If the current reduces to 1.5 amperes in 0.1 seconds, the induced EMF will be. So for a current of 2 amperes, the magnetic flux is 0.8 Webers. If it's for 1.5 amperes, we do not know. We need to find out the induced EMF. Now, the first time, so I1, that is equal to 2 amperes, and I2, it is reduced to 1.5 amperes. And flux in the first case is 0.8 Webers, and flux in the second case, we have to find out. And the change of the current happened in a duration of 0.1 seconds, so that will be the value for dt. Now, we need to know the fact that the magnetic flux is directly proportional to the current passing through the circuit. So therefore, we can write I1 divided by I2 will be equal to phi1 divided phi 2. And using this relation, we can write 2 divided by 1.5 is equal to 0.8 divided by, let's say, phi 2. So let's simplify 2 by 1.5 into 20 by 15 equals 0.8 divided by phi 2. 20 by 15 becomes 3 by 4. So 3 by 4 is equal to 0.8 divided by, or actually it's 4 by 3. It's not 3 by 4 because 20 divided by 5 is 4. 15 divided by 5 is 3. So it should be 4 by 3, not 3 by 4. My mistake. So 4 by 3 is equal to 0.8 divided by phi 2. And on cross multiplying, we will get 4 times phi 2 is equal to 2.4. That's because 8 times 3 is 24. So just put in a decimal, so you'll get 2.4. So again, the relation for phi 2 is equal to 2.4. Phi 2 is equal to 2.4 divided by 4. 6 times 4 is equal to 24. So 0.6 times 4 will be equal to 2.4. The value of phi 2 is 0.6 Webers. So now we know the value of phi 1, which is 0.8. We know the value of phi 2, which is 0.6. Now we need to find the change in flux. And the reason why, because the formula for EMFE is d phi divided by dt. This is for the modulus. That's why the right-hand side is positive. If it was for just the actual value of E, it'll be minus d phi by dt. But in any case, d phi means change in magnetic flux. So basically, we can just subtract the final from the initial. So therefore, it'll be 0.8 minus 0.6, which is equal to 0.2 Webers. And the value for dt, we already know, 0.1 seconds. This was given in our question, this part, if the current reduces to 1.5 amperes in 0.1 seconds. So that's where we found out the value for dt. So let's plug in the values. d phi is 0.2 divided by dt is 0.1. Again, multiply by 10 on both the numerator and the denominator. You get 2 by 1, which is equal to 2 volts. So the right answer is option A, 2.0 volts. Again, 0.0 is just a significant value, and that's significant figure. That's why they put it in. So 2.0 volts. It shows you the precision of the measurement. Option B, option C, and option D are incorrect because we found the value as option A using the relation between current and magnetic flux, which is a direct relation. And after that, we found out the EMF using the formula E is equal to minus d phi by dt. Again, we just took the modulus, so that we'll get a positive value. So 2 volts is the induced EMF. And that concludes this episode of NEET preparation. We hope you found this video interesting. There are a lot of questions on the chapter electromagnetic induction, and especially in electrostatics, there are many questions that are asked in medical entrance examinations. So don't forget to stay tuned by hitting our notifications button in order to receive more of our NEET preparation content. And if you want to support us and get access to more of our useful and interesting content, then don't forget to subscribe to our channel. The name of the channel is Brain Blitz Audios. So until we meet again, take care, stay strong, bye-bye for now.